If you combine that last video with the results that we had from Monday's videos, Monday night's release of videos, or Monday class videos, we really have a complete set of the elementary uh, optical transfer matrices. This is table 18-1 from my textbook and the class textbooks. That's on page 404 of chapter 18. It's table 18-1. And I wanted to point out a couple of things here that the we have a complete, really a catalog, I guess, if you will, of all the transfer matrices that we did earlier. There is a typo on this, and that's the main thing I wanted to point out here. This in this upper corner for the refraction matrix, that should be a 0, not L. And I think if you go back and look in Pergotti's book, it's a 0 there, and it was a 0 as we obtained it in class as well. That's refraction at a spherical interface. This is just translation from over a distance L. This is one of the first ones that we did, the refraction at a planar interface. You don't really need this if once you have this one, because you just let R go to infinity, as we've seen. And the thin lens matrix for the optical transfer matrix for a thin lens. And F is the usual thin lens focal length. It's valid, as it turns out, for a thin lens in media that has the same index of refraction on both sides, and n prime for it is the index of refraction of the lens glass. For a convex lens, F is positive. For a concave lens, it's negative, so there's a sign convention. And then the one we just got through doing is the spherical mirror equation, again with the convex being positive, and the concave, which is the one that's drawn here. So this would be you'd have to choose an R value to place in this formula that's a negative value of whatever the radius of that was. Well, with those, we can start to put all of these things together. So be sure to check for this typo. It may have been corrected in some later printings of the book, but at least the printing that I had, it was there. So make sure to correct that in your textbook. Well, next we'll launch into working an example and show you how these are put together. One other thing, probably while we're here, that I should point out, if you look at the determinant of each one of these matrices, it's pretty much, well, it's easy to calculate. The determinant of this one is just 1. The determinant of this one is the ratio n to n prime. That's the initial is on top, n is on top, and the final is on the bottom. Remember, this should be 0 here, so you only get the diagonal, so the determinant of that is n over n prime. And this one, determinant again, n over n prime. The initial index of refraction that you're going into over the final. For the thin lens, it's 1. And this one, it's also 1. And it turns out that the determinant of the transfer matrix is always simply the ratio of the index of refraction of where you started to the index of refraction to where you finished. So And you can see that that happens here. Here it's 1, but I'm in a homogeneous media, so it's the same index of refraction, whatever it is, at both the entry point and the last point. Same thing for refraction. It comes over here. It starts off in index of refraction n and ends up in n prime. And so the determinant is the ratio of the index of refraction where you started to where you ended. Same thing for the refraction matrix here. The thin lens, well, I started n, I wind up at n, and so the ratio should be 1 of the start divided by the final, and that's the determinant here. And likewise here, whatever index of refraction is on this side, you start off with that index of refraction and you divide by the index of refraction. So again, it's 1. So in general, the determinant of these matrices gives you the initial divided by the final index of refraction of the media that you're in for the entry and exit rays. Well, we'll apply that as a good way to check things.